Previous lecture we discussed a basic concept of ordinary differential equation. Also we discussed the first order, first degree, ordinary differential equation, and the first method, a simple separable variable method, and homogeneous equation. Now in this lecture we discuss exact differential equation. So what is the definition of exact differential equation? So if m and n are a function of x and y, the equation m dx plus n dy is equal to 0 is called exact when there exists a function f of xy of x and y such that d of f of xy is equal to m dx plus n dy. Again, I repeat, m and r a function of x and y. The equation m dx plus n dy is equal to 0 is called exact when there exists a function f of xy of x and y such that d of f of xy is equal to m dx plus n dy. The theorem, necessary and sufficient condition for the differential equation m dx plus n dy is equal to 0 to be exact if del m by del y is equal to del n by del x. So this condition del m by del y is equal to del n by del x is a necessary and sufficient condition for the differential equation m dx plus n dy is equal to 0 to be exact. If the equation is exact, m dx plus n dy is equal to 0 is exact, then the solution form can be written as integration m dx, where we consider y is constant, integration n dy, where the terms of n containing y only is equal to c. So if equation is exact, then the solution form is integration m dx, where y is constant, n dy, where the term of n containing y only is equal to c. Example. So first example we discuss, solve y square minus x square dx plus 2xy dy is equal to 0. Y square minus x square dx plus 2xy dy is equal to 0. Solution. Here, first we compare this equation with the standard form m dx plus n dy is equal to 0. So m is equal to y square minus x square and n is equal to 2xy. Now we find the partial derivative. So del m by del y. So del m by del y is equal to 2y and del n by del x is also 2y. Since del m by del y is equal to del n by del x, therefore the equation is exact. So we consider first this is m, this is n, del m by del y. That means partial derivative with respect to y, where x is constant. So y square derivative 2y, x square derivative 0, n dy, n means del n by del y, del n by del x. That means y is constant, 2x, x derivative 1. So answer is 2y. Both are equal, so equation is exact. equation is exact, then the solution form we discussed in a previous slide, integration m dx, y constant, n dy, where the n term containing only y only is equal to c. So integration m dx, m is a nothing but y square minus x square dx, n dy, but n we considered the term only where the term is depends only on y. But here n is a 2xy which involve the variable x. So we consider 0 dy is equal to c. Y square integration with respect to x, y square is constant. So y square 1 integration is x minus x cube by 3 is equal to c. So this is the required solution. Now next example, solve x cube minus y into sin x dx plus cos x plus 2y dy is equal to 0. So again the same procedure we discussed in a previous example. First we compare this equation with the standard form m dx plus n dy is equal to 0. So m is a x cube minus y into sin x, n is equal to cos x plus 2y. So therefore del m by del y 0 minus sin x, so minus sin x, del n by del x cos x derivative is minus sin x. Since del m by del y is equal to del n by del x, therefore the equation is exact. Hence the solution form m dx by constant n dy, where the term of n containing y only is equal to c. So m is a x cube minus y into sin x dx plus in n term only the term which is depends on y. So 2y dy is equal to c. X cube integration x raised to 4 by 4. Sin x integration is minus cos x. So y plus cos x, y into cos x. 2y integration with respect to y is a y square is equal to c. This is the required solution. Now next, integrating factor. So sometime a differential equation m dx plus n dy is equal to 0 is not exact. That means the necessary and sufficient condition is not satisfied. Del m by del y is not equal to del n by del x. So this equation is not exact. So it can be always made exact by multiplying with suitable function of x and y. That means a given equation whose form is m dx plus n dy is equal to 0, which is not exact. So we multiply with some function, then the non-exact equation is become a exact form. So such a function is called integrating factor. So integrating factor, that means the integrating factor can be used any non-exact equation is convert in an exact form. That means we multiply some function of non-exact equation, then the non-exact become in an exact, which is called such function which is called an integrating factor, whose short form is if. Although the m dx plus n dy is equal to 0 always has integrating factor, and there is no general method for finding them. They may exist infinite number of integrating factor of the equation. So again, this is very important things. Not only one not only one factor is integrating factor of any equation. There are infinitely many. That means some example, suppose we consider any equation which is non-exact, we multiply with x, then non-exact convert in a exact, we multiply with x square, then also convert in a exact. So not only one integrating factor, there are infinitely many integrating factor. Okay, there are some cases where we use for finding the integrating factor. So first 1 upon n, suppose equation is non-exact, and then we use this formula 1 upon n del m by del y minus del n by del x, and this calculation of this form which is depends only on x, then the integrating factor is a e raised to integration f x dx. So this is the first case. If we calculate this term which is depends only on x, then integrating factor is this one. Case 2, suppose we calculate this term which is depends only on y, then the integrating factor is a e raised to integration f of y dy. So the second case 1 upon m del n by del x minus del n by del y is f of y, then the integrating factor is e raised to integration f of y dy. Case 3, if the function, if the differential equation of the form m dx plus n dy, where m is this and n is this type of form is given, then the integrating factor is 1 upon mx plus ny or mx minus ny, where mx plus ny not equal to 0 or mx minus ny not equal to 0. So there are different cases for finding the integrating factor. So now we discuss some example. So first solve y square minus 6xy dx plus 3xy minus 6x square dy is equal to 0. So the solution here, we compare this equation with the standard form m dx plus n dy is equal to 0. So we can say m is equal to y square minus 6xy, n is equal to 3xy minus 6x square. Now del m by del y is a 2y minus 6x, and del n by del x is a 3y minus 12x. So obviously both are different. That means del m by del y not equal to del n by del x. So we can say the given equation is not an exact equation. Now equation is a non-exact, so first we find the integrating factor. So here we use the method 1 upon m del n by del x minus del m by del y. So 1 upon m, that means 1 upon y square minus 6xy, and del n by del x we know that 3y minus 12x minus del m by del y is a 2y minus 6x. The calculation form is y minus 6x. In denominator y is common, y minus 6x cancel, then the term is 1 upon y. That means the calculation of this term is only depends on y. So we use the integrating factor formula is a e raised to integration f of y dy. That means e raised to integration 1 upon y dy. That means e raised to log y. Then the answer is y. So y is the integrating factor of this equation. So obviously we multiply y with a given non-exact equation. Then the equation become this form, and which is exact. Also we check this term is n, this term is n, then we find the necessary and sufficient condition del m by del y and del n by del x, and both are equal obviously. So this equation is a exact equation. Now equation is exact, then we know that the solution form m dx where y is constant, n dy where term of n containing y only is equal to c. So m we know that y cube minus 6xy square is m, and n which is term depends only on y, but here also depends on x, also depends on x. So 0 dy is equal to c. So y cube integration, y cube is constant because y cube integration with respect to x, so y cube x minus x integration x square by 2, so 3x square y square is equal to c. So this is the required solution. Now another example, solve x e raised to x dx minus dy plus e raised to x dx plus y e raised to y dy is equal to 0. So first of all, we write in the form m dx plus n dy. So the modified equation is x e raised to x plus e raised to x dx plus y e raised to y minus x e raised to x dy is equal to 0. So this term is m, this term is n. So del m by del y is 0 and del n by del x is e raised to del n by del x. So this is the depends on x. The partial derivative with respect to x. So multiplication rule, x derivative is 1 e raised to x and then x constant e raised to x derivative e raised to x. So del n by del x is this. Now both are different. So we can say the equation is not exact and not exact. So obviously we find the integrating factor. So suppose we use 1 upon m del n by del x minus del m by del y. So 1 upon x e raised to x plus e raised to x. And del n by del x, we know that minus this. Del m by del y is 0. So both are cancelled. We get minus 1. So minus 1 we consider f of y. So integrating factor is e raised to integration f of y dy. So e raised to minus 1 dy and minus 1 therefore e raised to minus y. So e raised to minus y is the integrating factor for the given equation, one of the integrating factor. So now we multiply e raised to minus y with the given non-exact equation. Then we get this equation which is called the exact. Now equation is exact. So the solution form is m dx y constant n dy terms of n containing y only is equal to c. So m dx n dy, but n is term containing only y. So here we write y into e raised to minus y e raised to y. So y dy. This term we can't consider. This term is totally we consider. So integrate them. We use integration by part. So e raised to minus y constant. X e raised to x integration is x e raised to x minus e raised to x plus e raised to x integration is similar. Y integration y square by 2 is equal to c, and then we get e raised to minus y x e raised to x plus y square by 2 is equal to c is the required solution. Thank you. So in this lecture we discuss exact differential equation. If the equation is exact, then we use the solution form directly and we get the solution. If the equation is non-exact, so we find the integrating factor. There are some different formula for finding the integrating factor. So we use the suitable method, suitable case. We find the integrating